In most cases, first order differential equations can be solved. In these cases, it's possible to find an approximation to the solution. We will consider two methods here. One is slope fields. Now, slope fields, they actually provide an excellent way to visualize a family of functions, as you'll see in a bit when I walk through an example. Now, how do you draw slope fields by hand? First of all, set the derivative to in the differential equation to a constant. For example, dy over dx is equals to m, where this is the slope. And then you'll end up with equations. Those equations are called isoclines, okay, for different values of m. Then you draw this family of equations. Then you go along each isocline and draw hatch marks, all right, corresponding to the appropriate gradient. I show you how to go about this in a minute, okay? So don't worry about that. And then the plot of those hatch marks is basically what will be a slope field. Okay, so here's an example. Given a differential equation, dy over dx is equals to y plus 1, draw isoclines corresponding to m is equals to negative 3, negative 2, negative 1, 0, 1, 2, and 3. Now, what you're going to do is, like we said, you set this equation, dy over dx. So, dy over dx is equals to m. So basically what you're going to do here is we are going to, and remember, dy over dx is equals to y plus 1. So you're going to equate this equation to each of these values and find the corresponding equations and plot them. So for example, at m is equals to negative 3, if you plug m is equals to negative 3 here, remember this is equal to y plus 1. Keep that in mind, all right? dy over dx is equals to y plus 1. And what you're doing is you're equating that to m, all right? So if m is equals to negative 3 in this equation that I have just highlighted, then y will be equal to negative 4, okay? When m is equals to negative 3, y will be equal to negative 4. And then, so we can go ahead and produce these equations called isoclines. So at m is equal to negative 1, negative 2, y is equal to negative 3. Remember, I'm just using these values here for m, all right? So at m is equals to negative 1, y is equal to negative 2. At m is equal to 0, y will be equal to negative 1. At m is equal to 1, y will be equal to 0. At m is equals to 2, y is equal to 1. At m is equal to 3, y is equals to 2. So we have this, all these guys are what we call as isoclines, all right? All these guys here. Y is equals to negative 4, y is equals to negative 2. So what we are going to do is to plot them, all right? So we are going to draw this family of equations. These are what we call isoclines, all right? Okay, so what you're going to do is to draw them here. Now, may just need to use, right, maybe that color. All right, so back to my diagram. So this will be, oops, I really select the line. All right. Thickness, color, that is fine. Right. That will be my first one. That is y is equals to 2. And then this will be my next one. There's another one here. There's another one here. There's another one here. Okay, now remember, the first one here is for, this is y is equals to 2. Y is equals to 2. Y is equals to 1. Y is equals to 0. And so on and so forth. Now, one thing that I want you to keep in mind is that each of these lines has a gradient, all right? In fact, for the first one, this for y is equals to 2, the gradient is 3. So for here, m is equals to 3. Here, m is equals to, y is equals to 1, 2. Here, m is equals to, for y is equals to 0, m is 1. For y is equals to negative 1, m is 0. Okay? And these are the ones that we are going to use to draw those hatch marks. M is 0. And the other one, y is equals to negative 2, m is negative 1. And y is equals to negative 3, m is equals to negative 2. Okay? And the last one, m is equal to negative 3. So, when we start drawing our hatch marks, right, what you're going to do is they will provide the right directional field of the function. So, for the first line here, y is equals to 2, the gradient is 3. Remember here, the gradient is 3, the one at the top. M is equals to 3, which means the gradient of each of those lines is 3. So we'll just draw at any point on that line, the gradient is 3. Okay, done. The next one, the gradient is 2. The next one, the gradient is 1. The next one, the gradient is 0. Along this line, the gradient is 0. In fact, when a curve crosses, for example, when a curve crosses a specific line, then the slope of that curve must be the gradient of that isocline. Okay, I'll show you that when I work out an example. Anyway, this is negative 1. So that will be like that. That's negative 1. Negative 2, so slightly steeper. Negative y is equals to negative 4, that's negative 3. This is supposed to be negative 3, sorry. So that should be much steeper, which will be something like much steeper than the previous ones. All right, so this is a slope field. And you can see when you use the isoclines, it's actually easier for you to do that. And so what it means is that, for example, before I start drawing the graphs, let me just mention something here. For example, let me pick a random isocline, this one here. Use a different color. So for this one here, so when a curve, all right, for this one here, so when a curve crosses this line, all right, when a curve crosses that line, its slope must be equal to -1. So that's what guides you on how you're going to sketch a family of function on this. So when a curve crosses this line, okay, so, and remember this applies for each of these isoclines that we have here. So just to give you an example, let me draw some functions here. So I'll start with this one here. So when it crosses here, the gradient should be, as you can see, the gradient is -1, and here the gradient is -2, and goes like that. So the gradient has to be exactly what it's supposed to be. Okay? When it crosses that isocline, the gradient, for example, at this point here, the gradient is -1, the gradient is -2, and that is one possible function. Remember, all possible slopes can be joined to form a family of functions here. All right, so you can actually sketch a family of functions here. It just gives us an idea of how the function might look like. Another function that we can get from this could be something like this. So you have something like that, and you can see, oops, oh, I didn't mean to. Okay, so this one here, all right, that's another possible function that you can get from this, or I can also come up with this one. Something like this. And as you can see, when that curve crosses a specific line, the gradient should be what it's supposed to be on that line.